Okay, so in the previous classes, or previous lectures, we used to discuss about the step function or impulse function, ramp function, all of these were in time domain. Then we used to do, when it's connected to a system, we used to make that system like convolution and do the other things. So that was related to time domain, was in continuous time domain. And we discussed a little bit about discretes. We haven't discussed the convolution in discretes yet, so right now all the convolution that we learned were based on continuous time domain, and some of applications about the, again, like the discrete time domain, but not a lot. Then our next thing, which is, let's go to frequency domain and see how the frequency domain is, how we can convert any time domain signal to frequency domain. After that, we will see the benefits or the advantages of the frequency domain over time domain. Like, for example, one of the most difficult topics that we discuss in the time domain is the convolution, especially when we do the integral, or when we do like with difference areas, like the graphical convolution. Okay, so who likes convolution? Everybody likes it? Me neither, I don't like it. So the good thing about the frequency domain, the convolution will be, instead of integral, will be as multiplication of signals. We will learn this later, but the good thing again about the convolution, it will no longer see this kind of complicated integral, let's do this area and do this area and etc. We will no longer use it, and actually that's what we, in real life, we will not use this part of convolution. We will use frequency domain. Then the frequency domain will make the life much easier. So I think you might be familiar of Laplace transformation from circuit analysis. So sometimes in circuit analysis, in order to solve some circuit problem, you will convert time domain to phasor or to phasor domain, or sometimes whenever you have a transient circuit analysis, like first order, second order transient circuit analysis, I think you need to convert this to Laplace transformation. So I'm not sure, have you done this in circuits course? Second order?
We didn't do second orders.
First order?
We did first orders.
First order, you did use Laplace transformation?
Not in circuits.
Not in circuits, okay. So I think...
In ZBQ we did.
So you did it like in time domain? How do you solve the differential equation?
He'd give us like the equation for like the phase of capacitance. That would be like 1 over omega c.
Yes.
And then we'd use that equation.
Okay. Okay. So go to this. I mean, that's a special case. However, like there should be some cases like we can expand it more. So that's why I ask, because most likely depending on different courses or different universities can have different products, different courses. Because I've never taught circuit here. Then anyway, so what we will see in this course, we will try to solve some problems using Laplace transformation. So we will convert every element in this circuits into a Laplace, into frequency domain. Then we can solve this. We avoid any multiplication, or any integration or any differential equation, so we can use the Laplace transformation. Or another thing, have you taken Laplace in differential equation course? Okay, so you see that in the differential equation course, you used to do Laplace transformation to many things, right? So you didn't need to do the homogeneous solution, the general solution, and the other thing. Now, in Laplace transformation, it will make the life easier by doing some analysis, especially like, let's talk about the circuits. When we have the capacitor, we need the capacitor will be C dVc by the current will be C dVc by dt, or the inductor, I think the voltage of the inductor L di by dt, something like that. So there are some derivatives. Then in order to solve RC, RL, or RLC circuits, you will see some complicated integral, or not too complicated. You'll see some complicated math equations. Then frequency domain is this. So again, like Laplace transformation, we know you're already familiar with this, but here we will go more in how to make signal analysis or the signals into Laplace transformation. Like how to convert delta of t to frequency domain, how to convert u of t, how to convert r of t, and other stuff. then how to convert sine, cosine signals. So we will focus more on the practical thing, the things that we are using it in real life. That's different than what you've learned in the differential equation course, which is basically was like math, but here we'll go more in application of math. Okay, so let me write overall like today, which is 12/16 Friday, the readings page 85 to 95. Then next week, Monday, the readings, or basically we will go through exam 1 answers, or exam 1 return, we will return exam 1. And also, when we have time, we will go to page 85 to 95. Then for Wednesday, the readings from 95 to 98, sorry. Then on Friday, the readings is 98 to 99, and also it will be the due dates for homework number 6. So homework number 6, you can go to Canvas and see what are coming for homework number 6. I encourage you to start answering homework number 6 maybe after Monday. Okay? So maybe you can start today, but maybe you might have some concept that not fully covered, but it should be fine. If you start today, it is everything. Give it a try today. Okay. So overall idea, or the overall thoughts in this course, basically we will discuss Laplace transformation and application about Laplace transformation in RC circuit signals or RL circuit, transit, whatever. Then this we will most likely the second exam will be about Laplace and Laplace transformation and the application. Then we will go to next thing Fourier series, Fourier transform. Then this will be the third exam. So starting from now, we will go to we call it frequency domain, and that frequency domain basically can be divided into 3 parts. The first thing, Laplace transformation, Fourier transformation, and Fourier series. So you will realize later Fourier series and Fourier transformation and Laplace transformation are very similar to each other. But anyway, let's discuss today Laplace transformation and their application. Then when we have the time to go to Fourier, we will talk about it. Laplace transform. As a shortcuts, LT. So basically, when we have a signal x of t, we need to convert this into x of s. Most likely, which is in S domain or frequency domain, the function will no longer be function of time, it will be function of frequency, which is we call it S operator. And most likely, it will be uppercases. So x of t here was lowercase, while x of s uppercase, x as uppercase. Then how we do the conversion, most likely we will use this symbol as converts for Laplace transformation. I think you might be familiar with this from math. So Laplace of x of t will be x of s. And how we can find it, it will be as the integral between 0 to infinity, and we will write 0 negative x of t e power negative st dt. Okay? So again, what's s? The s operator. S is actually the s operator complex frequency. We are in frequency domain, but keep in mind it is complex frequency. In other words, it's complex number. So as a complex number, it need to have real and imaginary parts. So S equal to sigma plus j omega, such that omega is the frequency that we know, omega angular frequency, like 2 pi f, something like that. So it should be complex number, sigma plus j omega. And when we look at the integral, we will see the limits, or the integral limit from 0 negative. lower limits. 0 negative or 0 from left. Why we put 0 from left? We put it in purpose. It means that the time immediately before time 0. So what's the purpose of using this? Just to make sure that t equals 0 is included within the integral. Is included in the integral. That's the purpose we have. So when we make, for example, the integral of delta of t, then we will not say it's 0 because it's out of the limits. Then delta of t, when it's centered at t equals 0, it will be included. All of it will be included. That's the purpose of making it like this way. Laplace transformation, there are two ways of making Laplace transformation. The first way, based on the integral, is called between negative 0. From negative 0 to infinity, that's what I mentioned here. And this thing is called unilateral Laplace transformation. Laplace transform. Laplace transform. Then there is other definitions about Laplace transform from negative infinity to infinity. And this thing we will call it bilateral Laplace transform. So we have two ways. Most likely we will use this. That's our current. So just keep in mind, whenever when you read the textbook or you read other things like bilateral Laplace transform, they mean from negative infinity to infinity. While we will take only the unilateral, which is basically, we can assume centered at 0. Then from 0 to infinity, this is like as going unidirection. While from negative infinity to infinity, as going a bidirection, going from this way and this way. So anyway, we will focus only from the integral between 0 to infinity. Okay. So just keep in mind these symbols that we use for Laplace transform. Like this is the symbol for Laplace transform. Also, you need to know like these symbols, like the symbol delta is related to delta of t, something like that. And the star that we used before, this is new variables or definitions for a star, which is for convolution. Now we have this symbol, which stands for Laplace transformation. So whenever we say like this symbol of x of t, this means Laplace transform of signal x of t. Okay? That's how we do. Now, let's try to do some, to apply this integral, to apply this definition for different variables, different values. So let's try this example, example 1. We need to find the Laplace transformation of delta of t. How we can find it? Basically, apply the, because it's unilateral, everything we do unilateral equation. So basically, it is the integral from 0 left to infinity, delta of t e power negative st dt. That's according to our property. Then delta of t, any function, we call that the integral between negative infinity to infinity, delta of t, x of t, dt equals to x of 0, something like that. That's what we used to know before. Now the same thing can be applied here, but we need to make sure it is centered at t equals 0. Then 0 is located before 0 negative or after 0 negative, therefore it's included in the question. So the answer will be e power negative s times 0. Because in other words, it will be x of 0, which is e power negative s times 0. So it will be anything e power 0 will be 1. So the answer will be 1. Then starting from now, let's take it as a rule. Laplace transformation of delta of t equal to 1. Okay? here is x of t, here is x of s. Then, every time and whenever we need to do a Laplace transformation for delta, will be 1. There is no change about it. How about if delta was shifted? Like example number 2. We need to find Laplace transformation of delta of t minus tau, if there's a shift like this, such that t larger or equal to 0. How can we find this? Let's do the integral. The integral between 0 negative to infinity. Delta of t minus tau e power negative s of t dt. You see that it is centered at t equal t capital, t uppercase. Then since t larger than 0, it will be included within the integral period. So t is bounded between 0 negative to infinity. Therefore, the answer will be x of t. We just substitute. If we assume this as x of t here, the answer will be substituted as t. So, when you substitute this, it will be as e power negative st. And that's it. So, whenever we convert delta of t minus tau or minus t upper, whatever we call it, it will be as e power negative est. So when there is a phase shift, it will make exponential. So that's what we write like shift here. It will be as exponential. If we are dealing only with delta of t alone, it will be 1. If it is delta of t minus tau, since there is a shift, it will be as exponential e power negative est. Okay? Let's do more examples. How about from the other signals like this example number 3, u of t, Laplace transformation of u of t. Okay, how can we do it? Do the integral from 0 negative to infinity, u of t e power negative est dt. Since our interval between 0 to infinity and u of t here centered at t equals 0, this means u of t equal 1 when t between 0 to infinity, right? That's what we know about u of t. It will be 1 from t equals 0 to infinity, right? So therefore, we will replace u of t by 1. So it will be the integral from 0 negative to infinity, 1 e power negative st dt. Now, how we do the integral? Find this integral, e power negative est dt. It will be 1 over negative s, e power negative est, between 0 negative to infinity. Okay? That's how we know the integral for exponential. Then, 1 over negative s, e power negative s infinity minus e power negative s times 0. As we know for the exponential, but it is most likely look like this. So when you go to minus infinity, it will be 0, right? Exponential. When we go toward negative infinity, it will be 0. Therefore, this function equal to 0. So it will be negative 1 over s, 0, e power 0, 1. So negative 1 times 1 over s, this will make it 1 over s. So in summary, u of t, when we do the Laplace transformation, it will be 1 over s. That's it. Okay? How about shifted u of t? U of t minus tau. This is example number 4. We need to do Laplace transformation for u of t minus tau, such that tau larger or equal to 0. Let's do the integral. The integral from 0 to infinity, u of t minus tau, e power negative est deta. What we know about the exponential of u of t minus tau okay, u of t minus tau is actually equal to 1, I'm sorry, equal to 0 when t negative infinity up to tau, or it can be 1 when t between tau to the infinity. So we can split the integral period to be like this, between negative 0 to tau, u of t minus tau e power negative est dt, plus the integral between tau to infinity, u of t minus tau e power negative st dt. Now, we will say, based on this definition, u of t, we can apply it here and here. So we will say that u of t minus tau, when it is below than tau, t below than tau, this is equal to 0. Then this is equal to 1. Okay? So as a result, it will be 0 plus the integral from tau to the infinity, u of t minus tau, which is 1 actually, it's 1 e power negative st. Then let's do the integral. It will be 1 over negative s e power negative st, the integral period from tau to the infinity. So let's do the integral negative 1 over s, we didn't substitute, e power negative infinity t minus e power negative tau s infinity e power negative s tau. So after we substitute e power negative, this is 0, e power negative infinity every time equal to 0. Then it will be as negative 1 over s, 0 minus e power negative s tau, or in other words, it will be as negative negative will make it positive, 1 over s times e power negative s tau. Okay? So we can say that whenever we convert u of t minus tau, it will be 1 over s e power negative s tau. Okay? So I will say actually the first component, u, will make it 1 over s. The first shift t minus tau will make it e power negative s tau. Okay? That's how we do conversion. Now, we can use these results in our analysis. So we don't need every time to do the integral unless you see in the homework problems or the exam, whatever, explain or justify using the integral or like prove this thing equal to this thing. Otherwise, the results that we get so far can be used with us as overall as a result, and we can use it in our analysis direct. So for example, if I say find the Laplace transformation of 5 delta of t minus 6 delta of t minus 2 plus 5 u of t minus 2 u of t minus 3. Okay? So in order to do the Laplace transformation for this one, to find the Laplace 5, delta of t is 1, so it will be 5. Minus 6, delta of t minus tau, the delta Laplace transformation is 1. T of t minus 2 is, the Laplace transformation is e power negative 2s. Then plus 5, u of s is 1 over, u of t 1 over s, so 5 over s. Minus 2, u, which is 1 over s. Then times the exponential e power negative 3s. Okay? Then we can use these results in our assumptions. Okay, does this make sense? So now you know how to do the Laplace transformation in direct way, which is basically using these results, or you can prove this by using the integral formula. Okay, any question? Let's go more in details to see how we can get better results or some results that can be beneficial for us, and so we can avoid use these integrals in order to do Laplace transformation. So we can say this is example number, I think, 5. Example number 5. Let's do Laplace transformation of e power negative at times u of t. So how can we calculate this? Let's do the integral from 0 negative to infinity, e power negative at u of t e power negative st dt. What do we know about u of t? U of t, when t between 0 to infinity equal to 1. That's what we know. So we will replace it by 1. So it will be the integral between 0 to infinity e power negative at e power negative st dt. Now we can simplify since both of them are exponential. It can be as negative 0 to infinity e power the integral between 0 negative to infinity e power negative s plus a t dt. Okay? Let's do the integral. The integral of the exponential is easy to find, which is 1 over inside the exponential power, which is s plus a e power negative s plus a t, then between 0 negative to infinity. So it will be as negative 1 over s plus a. Let's substitute the exponential, which is e power negative s plus a times infinity minus e power negative s plus a times 0. Okay? So anything power infinity equal to 0, anything power 0 equal to 1. So it will be as negative 1 over s plus a, 0 minus 1. So the answer will be 1 over s plus a. Okay? Now, the result that we can conclude whenever we have e power negative at u of t, this is Laplace transformation will be 1 over s plus a. This means when you have any exponential, it will be as this fraction, 1 over s plus a. Okay? This is as a result. Okay, any question? So this results, it's helpful and we will use it a lot in our analysis. Now let's do more. Okay. Now let's do Laplace transformation of R of t. This example. Number 6. Let's do Laplace transformation of R. Or actually, if we're going to this, we're going to be consistent. So far, what we know about the results for Laplace transform pairs, x of t, here's the line summarized, and here is x of s. So whenever we have delta of t, the Laplace transformation is 1. Delta of t minus t uppercases, it is e power negative st. Whenever we have u of t, it will be as 1 over s. When we have u of t minus t uppercase, it will be 1 over s times e power negative st. And when we have e power negative at u of t, the Laplace transformation s plus a. This transformation case. Now, with these results, these results can be helpful for us, so we don't need to do the integral every time. Then we can use these results in our analysis. Then, actually, you can refer to textbook or go back to textbook, page 96 to 97. You will see table 3.1 and 3.2. These tables will summarize many procedures or many special cases like this are very important and some other situations. I encourage you to have a look at them because these are very important in how to do the Laplace transformation. Basically, when you do the Laplace transformation, you don't need to memorize those. The table will be provided to you. So the table should be provided to you whenever you have the exam, the quizzes, or whatever you have. Everything should be available to you with this table. So your role as an engineer to use these tools to solve this problem. So, I mean, the proof that the examples that we discuss here are very important, and the other thing, let's use the results. So you can see this is, like the pages here, this is the first part, which is related to the properties. So these properties we will go through it even later in today's lecture, and also in Monday lecture we will go to the properties. So right now it's not our scope to go to properties. Let's discuss this table. Then we'll go later to this properties. But I encourage you, table 3.1, 3.2, those are very important for you to have a look and know how we do the curves. So let's see the results. So the Laplace transformation of delta of t, 1. We already proved this. Laplace transformation delta of t minus t uppercase e power negative ts. So we already discussed this. U of t 1 over s, u of t minus tau e power negative ts over s, and e power at u of t 1 over s plus a. Then we have other features, like when we have exponential and we have this time shifts. So you will see that because of the exponential, because of this exponential, we will get s plus a, 1 over s plus a. Because of the shifts, you will get this exponential, e power negative t over s. Okay? So if you understand this, then it will be much easier for you to do the analysis. Now, whenever we have t u of t, it's 1 over s squared. That is. If you need to prove this, prove that t of t equal 1 over s squared, then you need to apply some either the integral or some other properties. Then t minus tau, u of t minus tau, because of the phase shifts, we will do e power t. And the other thing, basically, since it's like t times u of t minus tau, this will make 1 over s squared. So whenever there is a phase shift, we'll make exponential. Or, I mean, we call it time shift. Time shift. So t squared times u of t, because the square, it will be cubic and it will be 2. In other words, I would say, it's already been mentioned here, it is n2 minus n minus 1 factorial. Okay, let's see the other thing. When we have the phase shifts, or I mean the exponential, it will make a shift. When we have this exponential, it will make a shift, and since the square gives cube, or gives 2. Then, if we have t power n minus 1, e power negative 8 u of t, it will be n minus 1 factorial over s plus a power n. And you know the factorial, right? So we can conclude from this, if we need to calculate t cubic, t cubic u of t, it will be, the transformation will be as 3 minus 1 factorial over s cubic, s power 3 or 4, yeah, here n minus 1, okay, so it will be as n minus 1 equal 3, therefore n equal 4, so it will be as, again, fix this, it will be as 4 minus 1 factorial over s power 4, so it will be 3 factorial over s power 4, and 3 factorial equal 3 times 2 times 1 over s power 4, which will be 6 over s power 4. That's how we found t cubic u of t. And if we need to calculate, and we say t power 4 u of t, here n equal 5, so it will be 5 minus 1 factorial over s power 5. Then you can find the answer. And that's how we do with the rest. Then when we have sine, Sine will be omega over s squared plus omega squared. Then if there's a shift, that's how it will be. So most likely, you can have a look and read all of this, and then we will use them in our analysis. So when we do the analysis, you will have a look, you will have an access to this table. You don't need to memorize anything. Then just make the conversion based on this curve, whatever you have, and use these tools based on it. Then we can find the sine, cosine, exponential times sine, exponential times cosine, etc. Okay? While table 3.1 we will go to this later, but 3.2 this is very important for you to have a look and apply this. So now, let's go for an example. Let's assume we have the following signal as x of t. Basically, like this. This is T1, this is T2, and the amplitude is here. So our target is to find the Laplace transformation of x of t. How to find Laplace transformation for this one? This is in time domain, and I need to convert this to frequency domain. So it's not a good idea to do it with this form as what we see here in the graph. So the best thing is to convert this graph into an equation. After converting this to the equation, then we can do the Laplace transformation. So what's the equation of this graph? X of t equals to, there's a magnitude A, then u of t minus t1, and subtract from u of t minus t. Is this correct? That's how we do the signal. We just finished the exam on Wednesday, so I think you still remember how to find this. Okay. Now let's find the Laplace transformation for it. Laplace transformation for x of t. It will be as Laplace transformation for overall a u of t minus t1 minus u of t minus t2. So the factor a will be out. Will be out. Then the Laplace transformation of u of t minus tau. Since we have u of t 1 over s, since we have t minus t1, it will be equal to st1 minus a, because we still have a, u of t is 1 over s, then t minus t1 equal to st2. Or in other words, it will be as a over s equal to st1 minus equal to st2. That's the Laplace transformation. Okay? Let's do another example. Example 2 here. We need to find Laplace transformation of r of t. In that table, there is no r of t. Okay, what should I do? As we know, r of t is actually t u of t. Go back to the table. T of t is what? 1 over s squared. So it will be 1 over s squared. Or there is also something else that we can do if we don't want to apply t of t. We can look at table 3.1. Where is it? It's supposed to be here. There is a property t x of t equal negative d s x of s. So what does it mean? We can say that this is t u of t. Here we say or t u of t. It is actually negative d ds Laplace transformation of u of t. That's how we do the Laplace transformation. Or in other words, I can rewrite it as Laplace transformation t u of t equal to negative d over ds Laplace transformation of u of t, and it will be negative d over ds Laplace transformation of u of t 1 over s, and the derivative 1 over s will be negative. So here is negative, negative 1 over s squared, which will make it 1 over s squared, which is the same answer. This is another way if we really use the property, the other properties in the table. So you have either option. You can use the table that's tu of t, which is 1 over s squared, or you can use the property applying the derivative. So again, like the pairs, that's important for us because we used to have different type of inputs, which is delta of t will be 1, u of t 1 over s, r of t, now it will be 1 over s squared. How about the phase shift? Delta t minus t0, whatever, it will be 1 times a power negative t0s. U of t minus t0, it will be 1 over s times a power negative t0s. R of t minus t0 will be 1 over s squared times a power negative t0s. So you see, this is because of the phase shift, time shift. We got a power negative t0s. Okay? Does this make sense? Now, let's go to the properties. So basically, my target now to focus in table Laplace transformation property. Properties of Laplace transformation. Basically, this is in table 3.1. Let me go back here to table 3.1, and you will see there are several properties like multiplication by constants, linearity, time scaling, time shift. So I encourage you to read this. Now I'm going to go for some of them, while the others can be easy to follow. I'm going to, for example, multiplication by constants is trivial, so we need to explain it. Now let me discuss the linearity first. Then we will go step by step for that as well. But you are required to know all of what you see in 3.1 and 3.2 as well. So let me go through linearity. So property number 2 was called linearity. So linearity means whenever we convert ax of t plus by of t into Laplace transformation, it will be as ax of s plus by of s, which means Laplace transformation will be converted in number, will be in multiplication, will be an addition, can be as a linear, so it will be on both terms. So as an example, Laplace transformation of u of t plus e power negative t u of t. How can we solve this? Let's do it term by term. So basically it is the Laplace transformation of u of t plus Laplace transformation of e power negative t u of t. So the first one, Laplace transformation of u of t, as we know, x1 over s. The Laplace transformation e power negative t, go back to table 3.2, e power negative t u of t. Let's see that table. E power negative t u of t. E power negative at u of t 1 over s plus a. That's what we see. Since a is 1, it will be 1 over s plus 1. 1 over s plus 1. That's it. Because from that table, again, u of t 1 over s and e power negative at u of t is 1 over s plus a. Since a is 1, then 1 over s plus 1. Okay? So the overall formula is 1 over s again plus 1 s plus 1. This is written in the other way, but most likely sometimes we need to write it in a form called standard form. I mean here, so far the answer is that we are done with the answer. But how about if we say we need to do it in the standard form? The standard form means we need to write it as numerator and denominator. So we don't want the addition in the middle. So how can we make this? Basically, we can say 1 over s times s plus 1 over s plus 1 plus 1 over s plus 1 times s over s. Okay? So the denominator will be the same, which is s times s plus 1. Then the numerator will be as s plus 1 plus 1 times s, which is s. Okay? So as a shortcut, it will be as 2s plus 1 over s plus 1, or sometimes we can say 2s plus 1 over s squared plus s. So why I not like this? Because sometimes in our analysis we prefer to use it as denominator and numerator. You will only do it if and only if you need it. I mean, again, like our answer we should end at 1 over s plus 1 over s plus 1. We are done with the answer. But here I'm just saying that in case, if it is required to you, find this or convert this into the standard form, then we need to do it in this way. Okay? Now, there is something that when we have it in the standard form, there is something we call it poles and zeros. Something related to the, we call it function or the transfer function, as we will discuss this later. But now I'm going to go through a definitions called poles and zeros. So we said that function x of s was 2s plus 1 over s squared plus s. So we know this is called numerator. This is denominator. Then we said that roots, we can say that, roots of numerator are called zeros, which is when the function will be 0, within the denominator will be 0. Here I think I missed out this to us. Are called zeros. And if we need to plot this in the plots, you need to write it as O, because they are zeros. Then we will say roots of denominator are called poles, which is when this function will be infinity, when the denominator will be 0. So in the plot, we will make it as x. So let's look at this function x of s. We have 2s plus 1 equals 0, therefore s equals negative 1/2, 1 over 2. This is zeros. Poles, you have like s squared plus 1 equals 0, therefore, s plus s, therefore we will select s plus 1 equals 0, then s can be 0 or s can be equal negative 1. Those are called poles. If we need to plot them into the xy plane such that this is the real part of s, this is the imaginary part of s, we will see that the location of zeros when it is negative 1/2 here, the location of poles at 0 at minus 1/2. Okay, so there is a U address. Okay, so here's the location of poles and zeros. Now we are done. I think there is a little